So why don't we get started? Cool. So thanks everyone for being here today. So my name is Sita Seil. I'm an assistant professor in the mechanical engineering department. And I am very delighted today to introduce Dr. Astrid Layton, a fellow scholar and one of my good friends. She's an assistant professor and Donna Walker Faculty Fellow at Texas A&M University in the J. Mike Walker 66 Mechanical and Department of Mechanical Engineering. That's a nice mouthful for your department. She received her PhD in mechanical engineering from Georgia Tech Institute of Technology in Atlanta, Georgia. Her research, which we're going to hear about today, uses interdisciplinary collaborations to solve large-scale systems problems, developing knowledge that supports designers and decision makers. Dr. Layton is an expert in bio-inspired systems design with a focus on the use of biological ecosystems as inspiration for achieving sustainability and resilience in the design of complex human networks, systems, and systems of systems. Examples include industrial resource networks, power grids, cyber-physical systems, supply chains, innovation processes, and water distribution networks. So I think we'll have a great chance to be able to hear about that today. For those who are on Zoom, I'm going to be monitoring the chat, so please feel free to drop any of your questions in there for the Zoom folks. But without further ado, please go ahead and take it away.
Awesome. Thank you so much for having me. I'm really excited to be here. It's been a great visit so far. It's been really fun getting to talk to so many different researchers here and see what you guys are up to. I think you've got a really great department here, a lot of cool stuff going on. So yeah, this is my lab, the Bio-Inspired Systems Lab. These are current and former students, so these are not all current students. But the work I'm going to be talking about today is really, primarily done by these current and former students. So I wanted to give a shout out to them and, do some good advertising for them in case they're looking for jobs. But yeah, the talk for today, I'm going to be focusing on some different characteristics that we've found in nature and kind of try to validate adopting that in engineering design. So how do we design our systems to be more resilient and sustainable? There we go. So yeah, my lab really focuses on sustainability and resilience. We're not, not to the exclusion of everything else, but these are topics that we've been especially interested in lately. And especially this idea of how do we combine the two together? So, it's been one of my guiding principles is that, we can't, a perfectly sustainable design that's not going to be resilient to disturbances isn't a great design. So how do we really combine the achievement of these two things together? So that, really we're looking at not just environmental, economic, and social sustainability, but adding resilience to that goal as well. And we're doing this by taking a systems perspective. So, that we can work on all different kinds of detail-oriented problems, but, our decisions are much more limited. The solutions we can take are much more limited when we are taking this really small scale approach, looking at these little pieces of the overall system. But when we take this big picture systems approach, we really see a lot more opportunities to achieve goals like sustainability and resilience. So, opportunities that we can achieve economic sustainability, waste reduction, value retention, reducing our raw material use. A lot of these are only visible, right? We really only see them as possibilities if we're taking that system view. So that's what we're trying to do with a lot of these problems we've been working on. And when you take this system view, you can really find system problems anywhere. So we've looked at supply chains, water distribution networks, satellite networks, industrial resource networks, power grid, even larger systems of systems, all these different types of case studies to see where can we apply this biological perspective and maybe find a more unique, better way to meet goals. Again, we're doing this via bio-inspired design, sort of biomimicry. So this idea that we can find novel solutions, innovative solutions to different challenges we have by mimicking or drawing inspiration from nature. And sort of the underlying hypothesis that we're working from is that nature's had, billions of years of R&D. So why not take advantage of that and see what nature's kind of learned or come to the equilibrium, those states, what are their characteristics that we can use on the engineering side? And, there are a lot of efforts to sort of biologize things. I don't know if that's a real word, but, greenwashing is an example. There are a lot of places where you see this idea of, waste equals food, or eco thrown into the mix, or, something plant-based, comparing technology to biological cycles. This sort of idea of bio-inspired design gets thrown around a lot, but it doesn't always have real grounded meaning in, like, are we, doing extracting real value from the biological side and bringing that over to engineering. So again, eco does not necessarily mean like nature. And one of the big principles of my lab is we're looking for quantitative principles we can extract from nature and bring those over to engineering. So shifting away from the sort of qualitative side that you often see in bio-inspired design at a systems level. So these quantitative solutions, right? We're looking at biological ecosystems. So these are complex networks of all these different types of interactions happening in nature. Food web models are one way ecologists study ecosystems, where you just focus on those predator-prey interactions. And they've been able to link the structure of these food webs to the function of the food webs quantitatively. And they do this through something called ecological network analysis. It uses directional graph-based models of these predator-prey food web networks, and then matrix translations of that directional graph information to quantify characteristics, pick up patterns. So the analogy that we're using with our human networks is that our species in our food web are equivalent to the important components of our human network. So these could be industries, they could be grid components like a transformer or a bus. But the important thing is you've got an exchange of transformed material and energy happening inside your human network. So if you are modeling, so you wouldn't, for example, model a power line as a component if you're creating a grid food web model, right? Because that power line isn't actually transforming the material or energy, the energy that's traveling, it's just transporting it. Right? So this idea of like having your components transform or do something to what's flowing is really important. And then what we're working from is this idea that if we promote ecosystem-like features, we can gain some of their characteristics that are really valuable and desirable on the human side. So things like sustainable processes, resilient and robust to unexpected disturbances. This is something that both ecosystems and human networks have to deal with, right? Stability to actor deletions, having cyclic pathways so that you are using all available value in the system, and then supporting very specialized species, right? There are many cases where we have components in a human system that maybe are more specialized and less well connected to the overall system. So we want to make sure those are supported. So this is just like a small subset of the different types of ecosystem features and characteristics that we want to try to translate over to the engineering side. So I mentioned ecological network analysis. So just a brief high-level walkthrough what this process looks like. So basically you go through and select your ecosystem and you choose your system boundaries. So same as an engineering problem, right? Step one, choose your system boundaries. And then you're going to determine all the predator-prey interactions between the actors inside your system boundaries, as well as across the system boundaries. So you're tracking, useful system inputs, useful exports, valuable exports, as well as dissipation. All of those are captured. And then you're creating a directional graph or digraph where your actors become nodes. So in this case, the actors are species. And then those interactions become your edges or directional connections. So here we've got our directional graph version of this ecosystem, or food web model of the ecosystem. And then there are two different levels of analysis we can do in ENA. The first is looking at just the intercompartmental links, so things inside the system boundaries, and it just focuses on topology. So you can see that we've translated the topology of this system into a matrix form using ones and zeros. One means there's a link, zero is no, right? So we're going from prey to predator, kind of following that exchange of energy, right? So this is a food web matrix and just structural information. And then we can also look at flow magnitudes happening. Right? And in that case, we're including system inputs, system exports, so that's anything useful leaving the system boundaries, and then any sort of dissipation. And again, you're allowed to have sort of these cannibalistic self loops or self interactions. Yeah.
And how are the weights allowed to be non-unity?
So all of these weights, so what we have, the sort of guiding principle here is you have energy or material balance at each node. So whatever goes in equals whatever goes out. So basically your rows and columns, any row has to equal its equivalent column. Yeah. And if you have multiple flows, you would have multiple layers of this network essentially. So all of your units inside one matrix should be the same. So the first characteristic I kind of wanted to introduce to you guys is ecosystem cycling. So this talk will go through a couple of different of the most interesting characteristics we've worked on to translate from ecology to engineering. So ecosystems characteristically have a lot of cycling, right? And this has been related to their effective use of materials and energy inside the system. And detritivores and decomposers, these are things like, earthworms, slugs, fungus, anything that's breaking down dead organic matter, really low quality materials and energy. These are really critical to the overall ecosystem and this specific level of cycling. When we quantify the cycling going on inside ecosystems, we're using that first level, just the structure, so ones and zeros, only care about topology, which is really valuable for some engineering systems because sometimes you don't have detailed information, but you still want to learn about the system. So the quantification of this is the metric cyclicity. It can be a value of 0, which is no cycling. Value of 1, which means you have some level of weak or basic cycling. So essentially one loop going on inside the system boundaries. And then any value greater than 1. So the larger your value, the stronger and more complex your cycling is. Food webs are characteristic of very high levels of cyclicity, very high values. And again, this metric is going to identify your cycles as well as quantify the complexity and level of cycles you have. And we're looking for high values if we're trying to be bio-inspired. So we looked at this characteristic for industrial networks and specifically eco-industrial networks, right? So again, this idea of like eco being thrown around. We thought these are networks of industries that are purposefully trying to develop relationships where they exchange byproducts to reduce overall resource use, overall waste production, right? So they're really trying, they're trying to do the best. They've labeled themselves eco. Are they really eco, right? Are they really like nature? So we looked into what would an equivalent detritivore decomposer be for an industrial network. So we came up for a definition of that, right? So I had to deal with some kind of low quality material energy processing, and it had to be an active participant, right? So this was really important. It had to have stuff entering and leaving. And then we looked at all these different types of eco-industrial networks, the level of cycling they had, or the number of these loops and complexity, and then if they were successful, yes or no. So this is an example of a French eco-industrial park. We see there are 2 of these active detritivore actors, and we've got everything in green is interaction that's involved in one of these cycles. The cyclicity is 3.7. It's got more than 15 loops going on, right? But when we looked at the overall set of all of these eco-industrial parks that we had, 48, we compared them to food webs, and we saw that they're definitely not eco in like a quantitative real sense. They're not mimicking this critical aspect of what makes ecosystems or food webs really good at reducing raw material use, reducing waste output, maximizing value extraction inside system boundaries, right? So we've got our set of industrial networks and our food webs, totally different, right? Our food webs, we've got nothing at the 0 or 1 mark, right? We've got a lot of industrial networks at the 0 level, right? And the average was 1.5. So not great if we're trying to be eco, right? So we looked at, how could we use this as a design guideline, right? So how could designers take advantage of this? So we had a carpet recycling manufacturing network from Atlanta that we had data on, and we essentially said, can we make a bio-inspired version of this? What would it look like? So, we've got our network over here with all the different components, and we've got our existing flows of carpet in the network, as well as potential possibilities. So all of those different possibilities, both existing and potential, we had the optimization create a bio-inspired version, with cyclicity being one of the characteristics we were trying to mimic in nature. And so what was most interesting is that the two networks, so our traditionally optimized, maximize profit, right, minimize cost, and our like official version, still sharing the screen? Okay, it just, something popped up. No. So similar cost emission savings of both the bio-inspired version and the traditional version both achieve similar cost levels, but they got there a different way. So this is kind of cool, right? So this means that if you just use these biological principles to guide your design, you can still achieve profit if you care about profit, but the route you're getting there is different. So what else are we potentially gaining, right? What other characteristics are we gaining in addition to, this profit that we care about, reducing emissions? So this was really promising, kind of spurred us on to look at other characteristics. So one of those other characteristics is ecosystem nestedness. This is also a structural characteristic, a topology characteristic, and it's a linkage distribution metric. So it's a way to quantify how your links, how your connections are distributed. When we talk about nested versus anti-nested, or low versus high nestedness, it's a value from 0 to 1. If you are perfectly nested, you have this hierarchy, right? So you're gonna have one actor connected to everyone. The next one is connected to a subset of those. Next one is a subset of those, and so on. So you have some that are totally connected and some that are very loosely connected, right? And that connection has only to that most general actor. So this hierarchy forms. So the metric of nestedness focuses on where you're placing those links. So it makes it unique from sort of more common kind of network size or just number of connection metrics. And ecologists use this to predict extinctions in ecosystems. So high nestedness has been attributed to mutualistic ecosystems, so like a plant pollinator network, where you have a lot of interactions that are beneficial to both sides, and resilient mutualistic networks in particular. So when we think about this from an engineering perspective, we can think that high nestedness, right, maximizing our nestedness, would let us use the minimum number of links to maximize our value extraction. And this is really important because a lot of times links are equivalent to costs, right? If you think about a water distribution network, if you want to have more connections, you have to build more pipelines. That's really expensive. So this was interesting to us because we saw it as a way to improve resource reuse for maybe a set number of connections if you only had access to so many links, to try to redistribute those in the best way possible. So we tested this with an industrial water network study. So this was a hypothetical, realistic model. You can see kind of the little 9-actor network up there in the top right-hand corner. So we had 9 actors, we had 70 possible connections and 5 different qualities of water. So ranging from like perfectly drinkable fresh water down to, wastewater. So gray water would be somewhere in between. We kept production and consumption requirements constant. And then we looked at all the different possible designs where you could achieve those production and consumption requirements, and split them up based on their nestedness values. So again, from 0 to 1, we grouped them into 10 different bins, right? So 0 to 0.1 would be kind of bin number 1. And for each of those designs based on their nestedness, we figured out how much fresh water gets used in that scenario. Because then in this case, this hypothetical scenario, we're trying to minimize overall fresh water use. And what you see here, so we have exactly 200 network designs per nestedness value that we looked at. And what you see is that you basically have decreased resource use the higher your nestedness gets, right? So your resource consumption drops as your nestedness value increases. So if we have assigned a nestedness value of 0.7 or greater, right, which is again 0 to 1, pretty high nestedness value, you have a 50% chance of having a design that fell into the lowest possible freshwater import group, right? So basically, if we said 0.7 around here or greater, so all of these designs, you can see that nothing in that range produced a design that had high freshwater use. So everything black kind of mimics the fact that there were no designs generated that use high freshwater levels. If you were 0.7 or greater, you had a 99% chance of being in the 2 lowest freshwater import groups. Right, so essentially saying that if you use nothing else but nestedness to guide your design of your network, by maximizing nestedness, you're guaranteeing that you're going to reduce your overall resource use. But, we wanted to make it a little more realistic, again, because pipelines cost money to build. What happens if your the actors, the industries in your network are really far apart? Is it still a viable design principle or guideline for decision-making in that scenario versus where they're really close together? So we included cost and maintenance of pipelines, and we looked at 3 different levels of geographic dispersion. So close was about 800 meters apart, and spread out was 200 meters apart. And then we also looked at 3 different scenarios of freshwater costs. So we looked at essentially low resource abundance. So if it's really expensive to buy fresh water, would your decisions be the same as in the case where there's lots of fresh water available, right? And it's really, really cheap, right? Europe has a lot of scenarios where they're trying to reduce freshwater use, or there's just not a lot of fresh water available. Maybe there's high taxes. So trying to mimic these different types of situations to see when is maximizing nestedness or increasing nestedness a beneficial design guideline. And what we see is that for all the geographic dispersions, for expensive freshwater and kind of medium, moderate costs, increasing nestedness decreased your overall annual cost, right? So this case in the top that's not highlighted didn't really make a difference. So you're not costing yourself more by using nestedness or not using it. Only in the case where freshwater is really, really cheap, right? Like dirt cheap, did this not make sense, right? So in that case, having the higher nestedness values would cost you more than having a lower value. So this was really interesting, but we still wanted to dig a little bit deeper, right? What we saw with that earlier carpet network where we thought, you're achieving the same engineering goal through a different solution route, what else could we potentially be gaining there? So we thought, let's look at resilience. Let's look at what happens to these designs when something like a disturbance happens, right? Something goes wrong. And again, what we saw, so we went through and broke each pipeline in the network for each design and looked at how much extra fresh water would be required to still meet needs in those situations. So how much supplemental fresh water would have to be purchased to kind of keep everything going. And the high nestedness designs, again, had the best performance, right? So they needed the least amount of additional fresh water in those disturbance scenarios to keep everything moving, right? So this idea that we could be gaining multiple different types of beneficial characteristics by mimicking even just one ecological characteristic was really interesting. So another place that we use this idea of nestedness, this metric, but on a very different type of model, was with looking at engineering makerspaces. So we looked at Georgia Tech and Texas A&M and compared those 2 makerspaces over time, how students were using the tools in the space. And this sort of started with COVID. So we were actually looking to see if we could capture when the spaces started to recover from COVID and students started to come back, to see, can you use things like nestedness to essentially track if something goes wrong or if things start going right again. So for this, we actually use a bipartite graph model instead of that unipartite model you saw earlier with the food web. So in this case, we've got students and tools, and we're only looking at interactions between the 2 groups, right? So we only care about student-tool interactions. We're not looking at student-student interactions, tool-tool interactions. But we still got, the structural matrix representation. And so what we saw is actually when these makerspaces were the most nested, right? So when we saw big increases in nestedness, we found that, all of the students would be interacting with these generalist tools. So things like a 3D printer. Most students would interact with a variety of tools. And then you're going to see a few students interacting with the most specialized tools, the ones that really require a lot of training. And we were also able to see things like, when the COVID impact was felt. So when those restrictions that were put in place during COVID, students started using the space again, but at that reduced level. And then when the restrictions started to be removed. So we could see that quantitatively, which was really cool because traditionally these makerspaces are just tracked or monitored, understood via surveys. Surveys can be complicated to kind of sort through and see what's happening over time. So kind of the last characteristic I wanted to talk to you and share with you guys about is ecosystem resilience, right? So everything we had done been kind of pointing towards this aspect of ecosystems be really resilient to unexpected disturbances, right? Things like droughts and fires and a lot of the similar stuff that we deal with in our human networks. So if you think about it, ecosystems have evolved for survival. Again, invasive species, floods, lots of overlapping threats. And it turns out that food webs embody a really unique balance of redundancy and efficiency that has been quantified by ecologists in this directional graph form. And it's believed that this balance, this unique balance, is due to their need to be able to grow and develop when things are good, and resources are plentiful, versus needing to survive when you have these perturbations happening, these unexpected disturbances. Both the species and the system overall need to survive. And this balance helps you avoid being brittle and not able to grow and develop when things are good, but also helps avoid a stagnation. So the quantification here uses that flow matrix. So we're using both structure and flow-based information. So the metric is ecological fitness. So it's a combination of this value R eco, as well as its dependent variable degree of order. Degree of order, which is the one I'll focus on, can be a value from 0 to 1. When it's 0, we have 100% pathway redundancy. So all possible pathways are being activated. When it's a value of 1, we see pathway constraint, right? So essentially there's only one way to get from one point to another. There's only one path you could take. All right, so here we've got those two versions, and this is what they look like in those flow matrices. And then again, food webs are in between those two extremes, but not perfectly in between those two extremes. Right? So ecologists discovered this idea of the window of vitality, that food webs, when you plot it using this equation, they tend to cluster in this group in this range of degree of system order, kind of 0.6 to 0.21. Right? So it overlaps the balance point, right, 0.5, but it tends to favor redundancy. Right? So this is this unique balance that they're trying to achieve. So they tend to favor redundancy over efficiency. And from an engineering perspective, engineers were all about efficiency. Let's be as efficient as possible. Efficiency saves money, efficiency saves resources, saves energy, right? Even the sustainability perspectives focus a lot on efficiency. But again, this idea of like, we need to be considering robustness, resilience in our sustainability goals. So, maybe this balance is a way to achieve both those things simultaneously. So we looked at the industrial water distribution network example again, slightly different version, but we used this window of vitality to optimize the network. So we came up with a sort of bio-inspired version. So that's this triangle point. This was the cost-only version, that's red square. And then we also had a point in between the two where we had a weighted balance of cost and our window of vitality, right? So that's this red filled-in circle here. So we're kind of interested in something where you consider both goals. And the results showed us that the bio-inspired version definitely was the closest to what we see in nature, not just for our window of vitality, but also for some of the other metrics. But it also costs more, right? So it was kind of our motivating factor for looking at the in-between kind of weighted optimization, including costs. But really, all of these other, bio-inspired metrics aside, is that extra cost worthwhile? Because even the weighted one was slightly more expensive than our traditional design. So is that cost worthwhile? So we looked at disturbance scenarios for the designs. And what we saw was that both of our bio-inspired versions fared better in the disturbance scenarios. So again, we had this idea of how much extra fresh water would you need during a disturbance. So like if a pipeline shutdown. So we looked at connection breakage scenarios as well as after shutdown scenarios. And in all the cases, right, the bio-inspired versions were either the same as the traditional or fared significantly better, right? So that idea of extra costs being worthwhile, right? I think resilience is a way that we can potentially show that that extra cost is valuable to the decision makers, because sometimes the sustainability extra costs associated with those goals are a little bit harder to explain to decision makers because it's such like a long-term goal, and the people making decisions might only be in that role for a couple of years. They're not going to be around when those benefits are felt. So probably some of the coolest stuff we've done is apply this window vitality perspective to power grids, right? In Texas, very much so. We know about problems with power grids and how disturbances can impact it. I didn't learn this till I went to Texas and moved there, but Texas actually has its own grid, right? The whole US has 3 grids. Texas is the 3rd one, right? It's all by itself. Didn't want to deal with all the federal regulations, so they created their own little bubble. Well, that did not work out for us during the winter freeze we had recently. We had major problems with the power grid. So this is like very close to actual experiences looking at these power grids. So we've done a lot of work seeing what happens when we create bio-inspired versions of the grid, trying to move our power grids into that window vitality, okay? So trying to be more like nature from that degree of system order perspective. So here you see 5 different case studies we looked at. These are all standard case studies in power grid design and research. And we have both the traditional as the filled in icon, and we have the bio-inspired version, which was keeping all of the grid physics met and meeting all the needs of the users. How close can we get to that window of vitality, right? So you can see all of them, we move closer to them. Not all of them did we actually get inside the window of vitality. But what was the most interesting is that all of the bio-inspired versions improved performance over the traditional versions. So in power grids, they're concerned with contingency analyses. So NERC, the organization in the US that covers power grid reliability, requires N-1, which means if one component fails, the grid's still going to be able to function and meet needs. So we looked at N-1, we looked at N-2, looked at N-3, so where 3 components fail. And the number of violations that occur in the grid, you can see the drop, the decrease is shown here. So the decrease that we see in the traditional from the original, right? So the original had an X number of violations. The bio-inspired had a reduction, so that's what we're showing here. So 100% is what we want. That means all the violations we saw in the traditional grid disappear with our bio-inspired version. So very exciting. What was also interesting to show, and what we were curious about, because right, the initial pushback is, well, you're just adding connections. So of course it's more resilient. But when we try to get into this window of vitality, we are not just adding more connections, we're purposefully placing additional connections. So what you see here is kind of a study we did, small study, where we said, okay, we've got our original grid. What if you can add 1 connection? Can you use this to show where to place that connection? Right, so these are all the different places you could put that connection, and you could see that, trying to get into that window of vitality or increase our eco value, right? There are very purposeful places where you would put those extra connections to try to be more bio-inspired. So it's not just more connections is better. We've also compared this idea of using our eco or being in this window of vitality against really state-of-the-art ways of optimizing power grids. And again, we see that the bio-inspired version outperforms these state-of-the-art methods, which is also really cool. So we've got SCOPF and OPF are 2 methods that are used to optimize power grid design. So we're comparing our bio-inspired version to those 2 versions. So that for each of these case studies, and these are much larger case studies, right? So the largest one is 500 buses, right? So very large grid. The ones you saw in the previous study, the largest we had, I think, was 14 buses. So that was more of like an early stage where we had smaller networks. But yeah, the triangle is the bio-inspired. The circles are the traditional methods. And again, you see a drop in the number of contingencies, right? So lower is better. And again, this is highlighting that window of vitality. So even when we are in the window of vitality, we can make it better by using this bioinspired method. So the last case study I wanted to show you guys, again, is using this idea of the window of vitality, but on a more big picture, generic case study. So this was a hypothetical case study, a system of systems case study. So the case study developed had 3 tasks that had to be performed, and each task, there were 5 available systems that could be used together to perform the task. So all of our different designs, we had 38,000 possible designs that we developed, were different ways you could complete those 3 tasks using different combinations of subsystems. And there were some communication protocols, so some subsystems work better with each other than other. And then we had disturbance analyses that we did. So we tested resilience this way. And we looked at recovery in this case as well. So we looked at how the systems were able to recover after the initial disturbance. And what we saw, so we looked at linkage disruptions as well as actor disruptions. So you can think of like, if you disrupted one of these components, you get rid of S8, you get rid of all the connections connected to S8, both coming in and leaving. So the actor disruptions are like a more extreme version of the linkage disruptions. So what I want you guys to focus on is we've got this parade up front in all of these cases where we've got our resilience loss metric. So how much resilience did we lose during the disruption? And then we've got the cost of the network here, right? So more expensive, less expensive. So this parade up front is how much can you reduce your resilience loss for a specific cost, network cost. And what you see highlighted, the green points are the ones that are in the window of vitality. The red points are the ones on that Pareto front that are not in the window of vitality. I'm going to go through a couple slides. So we've got L-1, so 1 linkage being broken, L-2, 3 links breaking, and then we switch over to deleting whole actors. So this is 1 actor deletion, 2, 3, 4, and 5. Right, so kind of summarizing all of that, right? And these are all our disruption scenarios, and this is our degree of system order, right? So in between these 2 dotted lines, that's our window of vitality, our ecological window of vitality. So not all, what we saw was not all of the designs within the window of vitality are good designs, okay? But the ecological window of vitality contains 63% of the generated architectures that were on the Pareto front in each of these disruption cases. So you can think of this window of vitality as a way to down select designs very early in the design process without having to model these detailed disturbance scenarios, which is more of the traditional method of doing these things. What we also realize is that maybe there are different windows of vitality in addition to the ecological one for different types of engineering case studies. Right? So if we just look at this case, you've got like this narrower potential engineering window of vitality for this system of system case study that had 40% of the architectures, like the best architectures, right? So it reduced the overall designs, the 38,000 designs that we looked at, reduced them down to 40%. And those 40% were all in the Pareto front. So just a couple takeaways before we do some questions. Right, this takeaway from what I've talked about today and kind of what my lab is trying to do is show that bioinspiration offers potential methods to combine sustainability, economic goals, and resilience goals, right? So we can show how we can balance and achieve all these things together, how to consider resilience earlier in the design process. So again, using this degree of system order and this directional graph model, you don't have to do detailed disturbance scenarios, which requires already having sort of close to our final network design and knowing, are we modeling a cyber attack to this specific router? Are we dealing with a hurricane that has these specific attacks on these components of my network? So we can down select to our most resilient designs without going through all that detailed analysis. These methods can also help us understand how to do more with less, right? The whole idea with cyclicity, where we're trying to maximize resource value extraction. So once a resource is inside your system boundaries, how do you get the most out of it? How do you essentially not allow it to leave the system boundaries if there's still value left? So figuring out how to incorporate those detritivore, those decomposer type actors in your system. You know, using this idea of a window of vitality, maybe even beyond the ecological window of vitality, looking for different types of windows as a way to achieve resilience and down select for resilience early in the design process. And then the ability to connect all of these things to real world issues. So like geographic dispersion, resource availability, cost, emissions, you know, maybe even potential of severity of disturbances. Right, so the system of systems study I went through, you could see that shift in that Pareto front, and maybe you decide you choose your cost based on your tolerance for risk, right? If you're worried about, you know, N-4, so 4 actors going out, maybe not 1 actor going out, you can use this kind of choose how wide is my window of vitality, right? How much do I want to down select? Other stuff we're looking at now is more system of system applications. We're looking at multi-flow networks, things like a cyber physical power grid. How do we model and use these techniques at that level, increasing our detail on our economic and disturbance scenarios, and including some transient modeling as well for some of the validation. So with that, yeah, I would be happy to answer questions.
For those on Zoom, if you want to, I'll make sure to monitor the chat, and if you want to unmute, if you could just raise your hand, and then I'll make sure to give you a chance to speak. But why don't we start with questions in the room?
Just something quick. At the start of your talk, right, you were talking about like there was a degree of like cyclical score.
Yeah.
Is there a maximal value for that for a given matrix dimension?
Is that like there is, yeah. The larger your matrix, the more cycling you're going to be able to get, right? And the more complex that cycling is going to be able to be, but it's not like a perfectly linear relationship. So we found that we didn't need to normalize by that maximum value in those cases. Yeah. But yeah, in general, there is, the larger your network is, yeah, the higher possible values.
One that there's like an actual, like, if you fix the dimension size and there is just like a formula out there for the maximal possible.
Yes, there is. Okay. Yeah. And right, so what I showed was the kind of structural investigation of cycling. There is a flow version of that as well that we've looked at, that looks at like, of the total amount of resources that are moving through your system, from inputs to outputs, how much is cycled within the system, right? And so we're looking at using that for like circular economy type investigations to see, you know, can we choose designs that do a better job of keeping value cycling within the system? Yeah.
I have a question. Can you talk to us a little bit? You had a lot of really interesting areas of case studies, and they're all sort of different. And I'm wondering, and then the methods that you're using are inspired by ecology. You talk us a lot about what the ecologists do. Can you talk to us a little bit, maybe this is a meta question, on what are the differences and challenges or unique aspects that you've seen applying these methods, but in different areas like power systems versus the water networks?
Yeah, so some of the case studies, so like power systems, for example, that has actually been more fruitful because electrical engineers are really well organized with these standardized case studies of different size power grids that they have. And so we could run these dynamic validation scenarios to see how the different grid designs would respond to a disturbance. And again, really well established, these are case studies everyone tests their stuff on. So there were easy ways to kind of compare our work to current standards, new work, because everyone's testing on these same case studies. So that was really nice. The grid physics did add some complexity. Right? So it was not an easy task to just apply this bio-inspired approach. We had to kind of figure out how to merge it with the grid physics still being met. So that was all in collaboration with electrical engineers, right, who are power grid experts, right? So I kind of glossed over a lot of that. The water networks added this complexity of the fact that it's not inconsequential to build more pipelines, right? Pipelines cost a lot. They take time to install. They require a lot more maintenance than like a power line. So that added complexity for those. So that was like a different consideration that maybe we wouldn't have looked at for power grids because it's not as high concern as it is in like a water case. We've looked at supply chains as well. The supply chains added some interesting cases where we had to figure out how to incorporate storage into the ecological techniques, right? Because we noticed the ecological techniques, they're snapshots in time, right? So it was not obvious how to use storage, how to model storage for those scenarios. The system of systems stuff, just the having to really think about how your subsystem actors are interacting with each other, what their individual rules were. So like each case study, we chose specifically to be able to see a different aspect of these biological characteristics. Yes.
What other questions do we have? This is a quiet crowd.
You did such a good job.
I have one more question. This regards the nestedness. This might just be a conceptual question. Something you mentioned was that, a high degree of nestedness is associated with a higher degree of robustness in the system. But if something is very highly nested, meaning there's like a root to the whole network somewhere, and if you take that root away, everything collapses.
Yes. So
is that really more robust than an anti-nested network?
Yeah. So what you'll notice is I try to be very specific when I talk about resilience and robustness, that it's resilient to unexpected disturbances. It is not more resilient to targeted attacks. Because you're absolutely right. That, especially that perfectly nested structure, you very clearly have one highly general actor that if that goes down, the whole system might be in critical trouble, right? Or might just collapse completely. So the idea of like a targeted attack, very different, right? So what we looked at, these N-X scenarios, L-X scenarios, these all have to do with a random disturbance. So where you're not specifically pulling in more information to target like a critical actor. Yeah. So like this, the same thing with an ecosystem. They're going to be more worried about these random disturbances. They're resilient to these random disturbances. Whereas, you hear a lot, I think, in the news about invasive species. Those end up being more like targeted attacks, right? When we have problems with invasive species, there's like a very targeted actor in the ecosystem that is suddenly in critical trouble, right? So I'm from Pittsburgh originally. There's like a huge push there. I don't know if you have it here, if it's made it this far, but lanternflies. Do you have that here? Yeah. So there's like a big public policy information campaign about killing lanternflies because they lay eggs on trees and they essentially like eat the tree bark and are damaging all these trees. And it's looking really bad. So there are constant campaigns out there to get people to recognize the lanternfly, both the eggs and the adult fly, and what they should do, how to kill it. Basically, you just swish it with your foot. Like people are being lanternflies for Halloween, and they've made it this whole like big campaign to try to increase awareness. But yeah, those types of targeted attacks, these don't necessarily work. So we weren't interested in those scenarios. Yeah, but good catch. Yeah.
Maybe a follow-up on the question is because highly nested network prone to targeted attack. I'm just wondering, are those kind of networks still within the window of vitality, ecological window of vitality?
So that's a great question. We actually haven't looked at that. We haven't connected those two metrics to each other to see, yeah, if the highly nested, where the highly nested structures fall in the window vitality, right? And part of the reason we haven't done that yet is because nestedness is like a topology metric, and our ecological resilience stuff is a flow-based metric. So once you have your topology, there are still a number of design possibilities you could have based on where you assign, how much flow you assign over each link. But I think that would be a really interesting thing for us to look at. Yeah, so I appreciate the idea. Yeah, thank you.
So thank you for sharing these really interesting ideas. And I apologize if I might have missed this, but one component of ecosystems is that there's a history to it, right? There's a historicity where some things may not always make sense, but because there's sort of a historical component to it, that's kind of how things have been shaped. So I wonder if that also gets incorporated in some of your models. So for example, when you're talking about like the electrical grid system, it's like, there's one way to design it in a way that makes sense based on ecology, but you're also dealing with an existing infrastructure, and like, how do you kind of deal with that?
Yep.
That component?
Yeah, so we've been working from the two different perspectives. So the case where you have total control over it and you can do the design from scratch. And then also the scenario where you have an existing grid and maybe you have limited ability to do some small modifications to it. And so what you saw with like our investigation of like, if you only could add one link, could you use this to guide placement of that link, right? So that was motivated by that idea that you don't always have this top-down global ability to design the network from scratch. Because yeah, you're absolutely correct. Some of these methods are going to be more beneficial when you are in that position versus others where like you have an existing water network or existing power grid, and maybe you can make small modifications as, you know, a pipeline goes down. Maybe you can make at that point some adjustments, like let's place it somewhere else, or right, that gives you an opportunity for improvements. So we think these techniques are helpful in those situations. Yeah, no, great. I did not talk about that, so.
So had you compiled like a master matrix for compare all the different variables for these systems? Because it's a little hard mentally to try to translate from one system to another what factor would be considered.
So like
to another.
all
like water system, power system,
yeah.
energy grid,
yeah.
which variables play which role in
yeah.
system.
So we have looked at cases. So we've done a case study investigation where we looked at all the structural metrics possible, all at the same time to see like which combination of those metrics could be most valuable. You know, do we need to be like nature in all the metrics or maybe just a couple of them to achieve the same outcome? We putting all the case studies together. We have been able to show that like similar benefits are seen in different case studies using the same characteristic. But I don't think we haven't done any kind of like overall global compilation of everything together. Yeah, no, absolutely. I think so.
It was interesting that the energy grid systems have like a test that they need to be robust to n-1.
Yeah.
And I was curious with the other systems you looked at, two parts of the question, but with the other systems you looked at, were there also like general tests they had? Because industry must have come to some balance of robustness and efficiency for their best practice or requirements.
Yeah.
And then the other part is, do you see a way where like you can most convincingly convince industry to shift that priority?
Yeah. So the nice thing with power grids is they are governed by the government, right? So N-1 is like a government requirement. Like this is a critical resource. People need power. So at a minimum, all the grids have to have this minimum level of security. So something like industries, they don't have that like governing body where everyone has the same standard. So each industry is gonna be making their own decision based on stakeholder interests and needs, you know, current profit versus costs going on, climate, economic and political events. So that's much more chaotic. So we can, right, if you look back at COVID, all the issues that happened, you can very much see they were not prepared for resilience at all, right? Like no one foresaw that, I think, happening or was putting money towards protecting against that, right? So in terms of placing value on that, I think now that it's happened, it seems like they're much more amenable to saying, hey, there's economic value in protecting against these types of disturbances. And what I think is nice is that the resilience angle, you know, when we combine sustainability and resilience, and we show that you can kind of achieve both, the resilience angle makes it easier to stomach and like explain why you should pay a little bit more for those designs. And they happen to also get you the sustainability. So it's almost like a backdoor way to like achieve sustainability, I feel like. Yeah. Good question.
I think we have to wrap it up for the next class. So thank you so much. Can we please thank